Hello. So today I will be explaining uh, SAT 111 9.3D. So I'll be talking about the CPU implementation for 9.3D. So this diagram right here is given to us, and what I'll be using for the video today. So I'll be explaining everything that's happening in here and how the logic gates are being used in this diagram. I'll also be explaining the HDL code line by line for the CPU and how it applies in the diagram. I'll also give an overview of the HDL code, which will help us understand the whole concept. So first, before we look at of course, we already look at the diagram. I want us to go to the abstraction, right? Because looking at this, it's a lot. So we want to kind of like, because this is all the CPU, what's happening in the CPU. We're going to just look at how the CPU works in the ALU. So it's easy to understand. So how the CPU is running inside the ALU right here. So the CPU. So by looking outside of this is this. We can see how the CPU is working. So the instruction memories are here, and the data memories are here. And as you can see, there are three inputs for the CPU: in M, instruction, and reset. So so and then we have four outputs, which was write M, go to data memory, out M, address M, and PC, which will go to instruction memory. Okay, let's go down. So what I want to do is I want to talk about the API before we go into the HDL code. So the API is in this one, this is basically the M value input. So basically the RAM. So and this is the instruction, 16-bit. This is also 16-bit. This is for execution, instruction execution. This is to reset where it just tells the program to restart. This is the out M. So this is the M value. This is write M. And this is 15-bit. This is the RAM address of M. And this is the ROM address, basically the next instruction in 15 bits. So now that I explained the AMI, I'll explain the CPU diagram right in detail. I did a bit of what we just said, but I'll go in more detail with this one. So the CPU abstraction and now the CPU API, we talked about that. Now we'll go back to the CPU diagram and we see how everything works. So the ALU will give an output right here that can be written to the data memory. So to do that, the CPU must confirm what is going to write into the data memory, and the value of that will be stored inside out M right here. So in the ALU output, there will be an address of how it writes something inside the data memory. So the content will be stored inside the data memory after it's written. Then the output for the CPU that allows it to write content inside the data memory, and the value of the output will be inside write M right here. So after the program counter will be holding the next instruction, and the CPU will decode the instruction executed. So now we know what's going on in and out. So the next step is to look at the HDL code. So I wanted to kind of split it because this is it's just to explain it one by one. It's too big. It's really massive. So I kind of want to split into two pieces. So for this part one, I'm just going to talk about this part right here. So it's easier. So first, this is the code. So we have a NOT gate, an OR gate. So two NOT gates, an OR gate. Sorry, two NOT gates, an AND gate, and a MUX gate. So this can be seen in the diagram. Of course, you can't see the AND gate. Like it should be right here. But some parts are shown, so I'll explain it just like the AND gate right here. That's so you can see in the instruction, there are two types of instructions. There's instruction A, there's A instruction and a C instruction. So first, they need to decide whether it's an A instruction or C instruction. So the NOT gate is here. It's used to tell whether it's an A instruction. So a 16-bit code from the CPU would turn into a 15-bit. Yep. So if the code is 0, then the instruction is an A instruction. So if it's 1, then it's a C instruction. The instruction will move, the instruction right here will move to decode. And it will move to decode, and then it will go to the selective bit. So the selective bit's right here. All of these have a selective bit. So the selective bit will select the value between the code and the mux. So right here. And there is a NOT gate that can be used that's between the decode and the mux. Then the two inputs coming inside the mux, which is the instruction of the ALU out, and the selection that decides what's the output for the mux that goes to the A instruction. So the instruction goes here, decode it. So the select is the selector here. It stays there, and then you don't see the line, but it does jump to others, and then the value of ALU output come here, go to mux, and then this was the select right here, ALU to A. It will decide whether it's an A or C, and then it will go to the A instruction. So see, either it's the not. So these are basically just telling you determine whether it's an A instruction. So this part will say it's there as a placeholder for C instruction. So U to A, and this part will select which value. Select which value. So whether it's an A instruction or C instruction. So we go to part 2. So this part we're mostly talking about we're right here. So basically from part 1, we're around here. So we're mostly talking about this part. This down part will be talked about later, but mostly this part. So now we're looking at the OR gate. So the OR gate here, which is to load A if the A instruction or C instruction is fed into A. So the A instruction then takes the value that is used to store to the A register from the mux and the output from the OR gate. So in the code, it will load into A. The value will be out between 0 to 14 bits. All right, here got 0 to 14 bits, and will be seen as address M, which is A out right here. It's A out right here. So the mux 16 right here will have a value of A and M, and the selection is whether it's A or M, and the output is AM out. So AM out right here. The D register together with the mux output goes to the ALU, and you can see the D out right here, the D register, right here, D register, and it will load into the D register like a loop. So D register goes here to the ALU, and then it will go into a loop, and then give the output D from the D register. The D register goes here, the selected bit, right? It decides to go to out M as a result, if it decides to, and then it just goes back like this. So let's go to part 3, which is we're still talking about the ALU. So with this time, in this one, we're mostly talking about the 2 inputs that's going to the ALU. This part is talking about fully about the ALU. So the ALU is D out or AM out. So AM is right here, and this is D out. Let's go into these are the 2 main inputs going to ALU, and the ZX is the instruction. So this the selection bit will tell the ALU to pick. So these are all the kind of selective instructions that will be inside the ALU, and the output is either AL out or ZR out, right, or NG out, which will become here. And this part, so these 2 will go out here, will be a selection bit. This selection bit right here will go to right M, right? This will go here. Okay, so for the two OR gates, I'll explain that. And the AND gate, they're used to set up the ALU output. So it can write on the data memory. So the first OR16 right here is to help writing with the operations of the ALU, the ALU output, sorry. And the second one is the second OR, which helps the content of the data memory of the ALU output. And the final AND gate right here is just there for the CPU to write content for the data memory. So we got part 4. So part 4 is just, so we looked at everything here, right, from top. So the only we have left is from down here, from right M. So we know that we got the ZR and NG out into the right M. So this is where we're gonna talk about. So the program counter, we're mostly going to talk about the program counter, the PC here, is a register that has the address of instruction that will be fetched next. So the load bits of the program counter are determined by the jump bits and the ALU output that we got previously. So the HDL code is there to check whether the ALU output and jump conditions is there. So depending on the instruction, then the instruction is a C instruction, then the program will be loaded into the value and jump to a specified location. So for this code, this is if it's 0, then it will jump if it's 0. So this one is if it's negative, it will jump, right? And this is not 1 if it's positive, not 0 and negative, not 0 and non-negative, right? And yeah, this one's just using program counter, which is just a reset. Yep. So this is connected here. This program counter is reset right here. Thank you. Then that's all.